Amplitude-modulated radio, or AM radio for short, was developed in the early 1900s and was the first method of broadcasting sound via radio waves. Now, like all electromagnetic phenomena, AM radio can be described quantitatively using Maxwell's equations. In this video, we'll describe each step of the AM broadcasting process, from transmission to reception to playback on a speaker. As you'll see, Maxwell's equations can be used to describe and gain insight into each step of the process. This video is part of the Governing Rules video series. A small number of rules describe the physical and chemical interactions that are possible in our universe.
Hi, my name's Stephen Lieb, and I'm a professor in the Electrical Engineering and Computer Science department at MIT. And today I'll be talking with you about Maxwell's equations. This video assumes that you have a working understanding of all four of Maxwell's equations. We assume that you have seen them, made calculations with them, and understand the various terms, but not necessarily that you are an expert. You should also know how to use the right-hand rule to determine the direction of electric and magnetic fields. Our objective is to improve your ability to describe events and devices in terms of Maxwell's equations. This includes deciding which equation would be appropriate for any given situation. Let's begin with an overview of radio broadcasting. We'll be discussing AM radio, as it is probably the simplest sort of broadcasting. There are four basic things we need to look at today: the transmitter, which sends the radio waves themselves, the receiver that detects them, and the speakers that turn the receiver's signal into sound. This picture shows an overview of the process. The transmitting tower on the left produces radio waves that travel through the air until a receiver detects them and sends a signal to a speaker. The tower is typically about 100 meters tall, and the receiver is about 10 centimeters wide. The transmitter is a tall metal tower with alternating current attached to it at high voltage. In AM radio, the whole tower is electrified. The entire thing acts as the antenna, which is not true for all types of broadcasting, such as for FM radio or cell towers. This next diagram shows the radio waves as they move outward from the transmitter. Specifically, it shows the electric part of the electromagnetic waves. You can see their shape drawn in orange and their magnitude shown in black below that. Next, we have the receiver. The receiver is a set of wire coils. These detect the radio waves and transmit a signal to a stereo system so that you can hear the sound. Our final piece is the speakers, which turn electrical impulses into sound that you can hear. Now it's your turn. With a partner, try to describe where each of Maxwell's equations comes into play in this situation. It may help you to break the situation down, draw diagrams, write the laws down, consider the terms in the equations, and perhaps even redraw the pictures. Pause the video here to discuss and consider the possibilities. Now that you have had time to think, it's time for a discussion. Your professor will lead the class through sharing the ideas and diagrams you came up with. At this stage, we will not be deciding whether any ideas are right or not. The goal is just to get everyone's ideas out in the open. Pause the video here for the discussion. Now that you have had time to share some of your ideas, let's get an expert look at where Maxwell's equations apply to broadcasting. Make sure to note whether or not you thought of each of these situations as we described them. You may be missing some, or you may have even come up with a few more. We will return to your brainstorms in a minute. Let's examine the transmitting tower first. The AC generator will drive positive charges to one end of the tower and negative charges to the other. Using Gauss's law, we can surround each of these with a Gaussian surface. Our electric field lines will point outward from the positive charges and inward towards the negative charges. In addition, because this is an AC power source, our positive and negative charges will constantly be shifting from one end of the tower to the other. After many cycles of this, we will end up with an electric field radiating outward from the tower. That field changes direction every half cycle. Let's look at the tower again in a different way. If we consider the current rather than the charges, we know that it will be moving up and down the tower. To analyze the magnetic field the current creates, we can use Ampere's law and draw an Amperian loop around the tower. The right-hand rule will give us the direction of the magnetic field from this current, which will change as the current changes direction. As with the electric field, this magnetic field will oscillate and change direction with time. While we look at this view, we can also work in another one of Maxwell's equations, sometimes called Gauss's law for magnetism, or the statement of no magnetic monopoles. You can see that, like all magnetic field lines, the magnetic field lines created by our tower have no start point or end point. They wrap around the tower and connect with themselves. Let's move on to the radio waves. As they move, the electric field at each point in space changes. That leads us to the Ampere-Maxwell law, which handles changes in electric flux. The law states that a change in electric flux will induce a magnetic field. We can draw that in on our picture. When we look at the magnetic field, it also changes in time. Faraday's law handles changing magnetic flux and tells us that it induces an electric field. Again, the two fields are perpendicular. When our electric field reaches the antenna, we would be tempted to use the Ampere-Maxwell law again. We know that there is a change in the electric field, which would induce a magnetic field, but magnetic fields are not easy to detect. This method is not very useful. Instead, AM antennas rely on Faraday's law. Faraday's law states that changes in the magnetic flux will induce an electric field. As the electromagnetic wave passes through the antenna, the electric field in the loop will generate a current, which is easy to detect. We can plug this antenna into our stereo and, properly processed, hear the sound that comes out. Now it's time to look at the speaker. Here is some video from my laboratory at MIT. Stereo speakers are just one example of the kind of things that we work on for research in the laboratory here.
So tell me about how it works.
Sure. Well, actually, I'll show you first maybe, and then we can discuss what makes it work. But this is exactly the basis for your stereo speaker or for your headphones that you might use to listen to an iPod. And if I connect it to the speaker, we can hear that sine wave.
Very neat.
Isn't that cool?
So if I adjust the frequency here.
Now what you're doing when you turn that knob is you're changing how fast the signal generator makes the sine wave change.
Okay.
And when the sine wave changes, that causes the tone that comes out of the speaker to change as well.
Okay.
Very cool. All right. Now, the basic principle for getting this to work depends on the interaction between a wire that's carrying current and the magnetic field that comes, in this case, from a magnet. So if we start with a simple case, it's a little bit simpler to draw than the speaker. We might just think about a wire or a section of a wire, that there's a current I in this section of wire that has a length L. So I'm imagining that there is a magnetic field, maybe pointed this way, all across the section of the wire. So we know, for instance, with the right-hand rule, IL cross B means I'd point my fingers in the direction of the vector of the length of the wire, and then cross that in the direction of the magnetic field. I cross B, IL cross B, gives us the force, which in this case would be pushing the wire up out of the page and towards the camera. So the plan with the speaker is that we're marrying a coil and a magnet. So these two pieces work together in some shape in order to make the speaker work. So what I'm imagining is that the coil that's in the speaker might, for example, look like this. And I'm imagining that we could have some current I in this wire that might be at some value as a function of time. So it could be here. at some point, so that's a positive current going into the wire. The other critical piece that we need to make a speaker is the magnet. And if I happen to have it oriented so that the north pole of the magnet is at the top and the south is at the bottom, then we can solve using Maxwell's equations to find out that the magnetic field comes out of the north pole and goes around and comes back to the south pole. And that picture's getting a little confused. So I'm going to make a little bit of a blow up of it so we can see what's going on any particular wire, if that's okay. This magnetic field has two components. One component is up, and the other component is in the radial direction. And that over piece in the radial direction is going to be spilling out the coil all around in all the radial directions. So this particular configuration means that there will be a force down on that section of wire. And it'll be down all the way around if I follow that around the radial direction of the wire. And so this coil, if you will, or this coil, if I were to pick it up physically, and if it were to have current and magnetic field as I've drawn, this coil would experience a force down. This is the situation as I've drawn it for a positive current. But if the current didn't always remain positive, then it might do something else. It might go negative.
So if it's positive, you'd get the downwards force, and if it's negative, you'd get an upwards force and repelling.
Precisely. So when the current reverses direction, but the magnetic field stays the same, then we're going to reverse the right-hand rule calculation, and now instead of the force being down on the wire, it's going to be up for the situation where the current is going around the other way.
Do you have a way to demonstrate this that we could see?
I definitely do. We've already seen it at work on the speaker, but I kind of have a speaker that's laid out or opened up. This was made by one of my students, Doug Adams, a very clever project. So I have a coil of wire that he put together here, and that coil of wire is wrapped around a paper form that's just glued to a styrofoam lunch plate. And you can see that coil can move up and down, and the coil can ride on top of a silver magnet. So if that works, we should see this plate experience a force up and down, as the sine wave goes plus and minus, plus and minus. And of course the neat thing with that is, with the signal generator here, I'm able to control how fast that happens. So if I press this button, I can make the signal generator change the current faster. And I can go even faster. And now, with just a paper plate, a coil, and a magnet, we've reproduced the function of the loudspeaker with a lunch plate. Pretty cool, right?
That's really great. Thank you for talking us through that today.
My pleasure. Thanks a lot.
In general, we have two categories to consider. A charge or a current can create a field, and we use Gauss's law or Ampere's law to investigate. If we have oscillating fields, we switch to Faraday's law or Ampere's law with Maxwell's extension. We also can't forget the Lorentz force law. While it's not one of Maxwell's equations, it's still very important to the study of electromagnetism. Now it's time to return to your brainstorms. Your professor will lead the class in a discussion and examination of the brainstorms you presented before. Remember that there are many different ways in which Maxwell's equations can describe electromagnetic phenomena. Just because something on your list was not on our list does not mean that you were wrong. I hope you appreciated our discussion of radio today. Good luck in your further studies of Maxwell's equations.